we didn't get to is talking about what happens as you get further and further into the sequence. And to say that in math, we say the end behavior, and it's kind of very similar to horizontal asymptotes. What's happening as it's getting really big and really small. And there's some new vocab words here that you need to know by the time that we have a test next week. And those words are converging or diverging or diverging, however you have to say it. If a sequence converges, we say as you go to infinity, as you go to the infinite term, or as x goes to infinity, the sequence is actually going to reach a specific number. So it's going towards 7. It's going towards 0. It's going towards 1. And I'm going to show you how we can figure that out. It's not a horizontal asymptote, but it's a very similar thing to that. And I'm going to show you that relationship. If you remember the rules of how do you find horizontal asymptotes, then you can remember this. What's wrong, Sean? You need new notes? The other option is if your sequence diverges, which means that as n gets bigger, you don't reach a number. Either your sequence is getting really, really big or really, really small. On your homework today, the other 5 problems that I didn't assign to you yesterday says, does the sequence converge or diverge? If it converges, give the number. Which means when we have a test, you're going to see the same types of questions. You have to know the difference. You have to know converging means going to a number, and diverging means not going to a number. So that's a vocab thing. Today you have your notes that you can look at, but on the test you're not going to have your notes, so make sure you pay attention to that. Okay, so let's just look at a few examples of this. This is exactly what your homework says. And it's really not that bad, so adding 5 homework problems tonight isn't the worst thing in the world. I'm going to show you a nice way that you can show this every time, and then we'll talk about maybe could I figure this out without doing that work. This is just a lovely sequence, 1, 4, 9, 16, ... This is the formula for the nth term. If we wanted to find the 5th term, we plug 5 in here and we get 5 squared. Right, so this is like the explicit formula. We want to know what happens as n gets really big. So we want to think about what happens as n gets very big. Some people are just going to be able to think about what happens. If you want a nice way to check every time, I suggest checking some lovely numbers, like 10. What happens when n is 10 in this problem? I would get 10 squared, which is 100. If it just said the square root, the way it's written, you take it as the positive square root. Like, you don't put plus or minus in front of a square root unless you're solving an equation. When you're solving an equation, if you take the square root of both sides, that's where we do plus or minus. But just written in a formula, if it said the square root, you only take the positive side. Does that make sense? So when n is 10, I got 100. What happens if I go even bigger? What happens when n is 100? I would get 100 squared, which is 10,000. 10 and 100 are my favorite numbers to pick because they're pretty easy to plug in most of the time. And there's a pretty big difference there. We could even go one step further. What if I plug in 1,000 here? 1,000 squared is going to equal 1,000,000. Would you say this sequence, as n gets bigger, is my answer going towards a specific number, or is it just keep getting really big or really small? Do you agree that this just keeps getting bigger and bigger? The bigger number I choose for n, am I going to keep getting a bigger number for n squared? Yes? Maybe you could have thought about that just from looking at this, n squared. It's just going to keep getting bigger no matter what you plug in there. So we could say, mathematically speaking, as n goes to infinity, a sub n is also going towards infinity in this one. It's not going towards a specific number, and that means, our new vocab word, that it diverges or diverges. It doesn't reach a number. And my advice to you is, if you're not sure, do this, pick 3 numbers. My favorite ones are 10, 100, and 1,000, and see what's happening. Because if it's going towards a specific number, we should see what's happening there. Like number 6. This is a lovely sequence. That wouldn't be very much fun to find the first 8 terms, but you could do it. What's happening as n gets really big in this one? And again, how do I do it? I'm going to plug in 10. I'm going to plug in 100, and I'm going to plug in 1,000. You can pick whatever you want, but don't pick really small numbers, because you're not trying to see what happens really small. You're trying to see what happens as n gets really big. And if I plug 10 in there, I'm going to get, on the top, 30 minus 1, which is 29, over 2 minus 30, which is negative 28, negative 1.035714. When I plug 100 in there, I'm going to get 300 minus 1, which is 299, over 2 minus 300. See, another reason why I like these numbers, it's usually pretty easy to do, which is negative 298. And if you divide that out, you get negative 1.0033557. And usually, by 1,000, maybe you don't even need to go to 1,000. You're going to be able to see if this is approaching a specific number. We're going to get 2,999 over negative 2,998. And I get negative 1.000333556. Would you say this is going towards a specific number? Negative 1, right? Because from 10 to 1,000, at 10 it was pretty close to negative 1. And then all the way to 1,000, think of how many terms are in between there. It's still negative 1.000333555. Like, it's really, really close to negative 1. So we could say that this converges to negative 1. And that's how they want you to write it. Like, it's converging to negative 1. Questions about that? I want to relate it back to horizontal asymptotes just because, one, we have a final coming up, and the whole rules for horizontal asymptotes are going to be on there. What if this was an equation with x in it instead of n in it? Do you remember how we find the horizontal asymptotes of a rational function? Like the degree of the numerator and the degree of the denominator. That's vertical asymptotes. Horizontal asymptotes. Remember, like, if the numerator is smaller than the denominator, then the horizontal asymptote is y equals 0. If the numerator is equal to the denominator, do you remember that rule? It's the leading coefficients. Look at my leading coefficients in this one. 3 over negative 3. What's that work out to be? Negative 1. It's not a coincidence that this is negative 1, and if this was an equation with x in it and we graphed it, it would have a horizontal asymptote of negative 1. Because both horizontal asymptotes and converging has to do with what happens when x is really big, n is really big. Same idea can work on this one. What if this was an x? Was x squared, is it going to have any asymptotes? X squared, it's a parabola. Does it just keep going forever? So if you think about it in terms of horizontal asymptotes, you can get the answer without necessarily doing a lot of work. So that's just something to think about, comparing 2 different things that we've done. Do this one if you haven't already. Check what's happening. Or think about what the horizontal asymptote of this would be. I don't know, just to confuse you. This is how they write it in the book. It really means nothing. It's just This has to do with the test we just took in chapter 3. This is an exponential function. Maybe you remember what asymptotes are on that one, but 0, 0, 0, 9, 7, 6, 5, 6, 2. So this one doesn't converge because this is really small and this is a really big number, right? Oh, right, scientific notation. We probably should make sure that we're reading scientific notation, but I just want to throw that out there. Some people only look at this and they say, oh, it's not converging, it's not the same number. Scientific notation, this is a negative exponent, so this really means there's like 31 zeros, 30 zeros in front of that. That's a really, really small number. What happens when you plug 1,000 in there on your calculator? Is it really 0? It's just your calculator runs out of the biggest or the smallest number your calculator can write would be something to the negative 99th power. If it's bigger than that, my calculators don't do that. So it just rounded it down to 0. But it's technically not 0, but it does say that it's 0. I'm going to say squiggly 0 because it's not really 0. But do you agree that this one is converging? Well, your calculator can just only do so much. Just like if you take 2 to the 1,000th power, and it'll probably say overflow error. Like it doesn't even round it. Because it's such a big number, if it's times 10 to something bigger than the 99th power, it can't do it. Like the calculators only have 2 digits over there for it. So if it's something to the times 10 to the 100th power, it says overflow. I can't handle it. It's too much math. But we could say that this converges to 0. Again, relating this back to horizontal asymptotes, if this was the equation, y equals 0.5 to the x power, every exponential function has a horizontal asymptote, and it always starts there at 0. So again, if you can think about horizontal asymptotes, you can always get the answers to this. Oh, we have a whole nother packet of notes.
What?
That was just left over yesterday. Crazy kids? Come on now.
I was so happy I was going to get to work on homework, and you're just like, no, Sean, crush. So I just punched the table.
So, we have 5 problems left on this. I'm going to write it at the end, but yesterday you should have done 1 through 4, 6 through 10. So today, in addition to day 2's homework, you're going to do 12 through 20 even. We'll write that again at the end of these notes. But some people in second hour were all concerned about keeping it all on the same sheet of paper and, I don't know, some crazy stuff. But anyway, there's 5 problems over converging and diverging, which are pretty easy to do. And then we're going to jump in here to day 2 notes, which is still the same section. I just split up my set. You're missing one? And it's really not so bad. You might even still have some time for homework, Sean.
Can I just give you the obvious answers?
They're different numbers. That's not what I want to hear.
No, Michelle, you say
There's not 2 to the second power on the top, though, right? Okay, so yesterday we just talked about, in general, about different sequences. Today we're going to get specific about writing our own formulas and what are the differences between the 2 main types of sequences. What is happening in this sequence? If you were back in grade school and you had to say, what am I doing each time to get the next number? What would you say?
Adding by 2.
Yeah, you're adding 2 each time. As opposed to this one, what am I doing each time?
Multiplying by 3.
That's a good little unison answer there. The difference between these 2 is if you add or subtract a number every time, those are called arithmetic sequences. Doesn't that make you sound so fancy when you say it like that? We don't say arithmetic sequences. That's not educated. We say arithmetic sequences. Arithmetic. Because you're adding or subtracting. As opposed to this one, if you're multiplying or dividing, which is still multiplying by a fraction, We call these geometric sequences. And basically, there's a bunch of different formulas that if you know it's an arithmetic sequence, then you can write your own explicit formula and your own recursive formula. And if it's a geometric sequence and you know that it's geometric, then you can use these formulas. And basically today we're just going to practice this. And the nice thing is I printed them out for you, and so that we can get it all in, and so you don't even have to write it all down yourself. How about that? Just because I'm that nice. I'm mostly just stressed about getting our test in time. Like, our finals are really soon. Second hour's final is the first day of finals. So really next Wednesday is like the last day that we could have a test. Because then that only gives us 3 days to review in there. And then your guys' is the next day, is the second day of finals. So, whew, I'm stressing. I got to get through this stuff. I don't know what happened. Last year we got through chapter 9 and then spent a week working on a final project before we even started reviewing for the final. And I don't know, we're just like a week behind again.
Okay, AP Bio and then AP History and this class on one day. That's almost as bad as having both of my math finals one day.
Okay, forget about finals for a minute. Let's focus on this. Any arithmetic sequence, if you look back at that one on the other page, 2, 4, 6, 8, 10, you could write it like this. If A is the first term, you could take A plus whatever that common difference is, which was 2, for the second term. Like, think about this was 2 on the one on the previous page. 2 plus 2, didn't that give me 4? That's my second term. This would be 2 plus 2 times 2, or 2 plus 4 gets me my next term. 2 plus 6, right? Or they could summarize it like this. If you take A plus whatever term you're on minus 1 times D, you will always get the nth term. And I kind of summarized all this for you here. It's all in your book in a lovely little green box, I think. D is what we call the common difference. It's what are you doing each time. Usually pretty easy to figure out. And what you're going to focus on today is you're going to write these equations, and I'm giving you the formulas. In any arithmetic sequence, the nth term can be written using this formula. You take the first number plus n minus 1 times the common difference, and you get your explicit formula. We're also going to write recursively defined sequences, which is even easier to do. You take the nth term is equal to a sub n minus 1 plus your common difference, but you have to say for n greater than or equal to 2. And all you're going to do is practice using these formulas today. It's really not so bad to do. And as we get closer to the test, we'll talk about formulas and am I going to give you formulas and all that fun stuff and all that jazz, but it's really not so bad. The great thing is on your homework today, it's like parts A through D on the problems. Isn't that exciting? I know you're excited. Oh, no, that's not those 5. That's yesterday's homework that we have to add on to. The other ones today, you get to do that. But it's not so bad to do. It looks like a lot of stuff. But this is what it says on your homework today. Part A, we're going to find the common difference. That's really easy. You're just going to say, what am I doing each time? They want to find the 10th term. I feel like that should be letter D, and we'll come back to that in a second. And then we're going to use our formulas that I just gave you to come up with a rule for the nth term and an explicit rule for the nth term, recursive and explicit. So looking at number 1, could you tell me what the common difference is? Could you tell me what am I doing to get from one number to the next? Adding 5. Right, everyone with me on that? So part A, the common difference is 5. What would my common difference be if I was subtracting 5? How would I write that? Negative 5. So if you're subtracting, then you have to put a negative. But if you're adding, then you keep it as positive. The 10th term. Could we find the 10th term right now? We could. We could just keep adding 5. But let's wait. Let's use our rule later. So I'm going to skip part B. It's okay if you go back to it. Because that's That's how the book writes it. So I try to do the examples just like the homework, so that when you get to the homework, you have a lovely example to look back at. Part C, write a recursive rule. Use that formula I just gave you. I'm going to write it out for you again. The recursive rule is A sub n equals A sub n minus 1 plus D, but you have to say starting at n greater than or equal to 2, just like the ones from your homework yesterday. They tell you where to start. What's the only thing you're going to have to plug into that formula? Because they have to give you the first term when they're giving you a recursive sequence, always. So like if we were doing this recursive sequence, we would say a sub 1 equals negative 4. And then we would give this sequence. A sub n, am I going to replace a sub n with anything? That's just my formula. It's just like y equals. I'm always going to leave that. What about a sub n minus 1? Think about what we did just on the homework number 10 and number 8. Weren't the problems written like this? Like those were kept in the formulas? But it always told you what to do here. All you got to do is plug D in here. Right? I can say a sub n equals a sub n minus 1 plus 5. Which means, what am I saying to do? To find any term, take the 1 before it and add 5 to it. That's a recursive sequence. You have to use the 1 before it. Yes? No? I feel like people are very confused by this for some reason. I like the explicit formula a lot better because you can find any term with it. But honestly, the explicit formula takes way more work than this one. This one, every time, all you're going to do is replace D with 5. Everything else stays the same for every recursive formula of an arithmetic sequence. But for part D, when it says find the explicit formula, and again, I'm going to write it for you because this is our first one that we're doing. The formula says A plus n minus 1 times D. I'm with you, but this is just an example, like they're just giving you the sequence. But anytime you're writing a recursive sequence, if you were really going to write that out, they wouldn't give you 4 terms. I see what you're saying. Since they give me 4 terms, you're saying, let's just say, let's start with, really we would start 5, right? I see what you're saying. But if you want to say that, you can, but that's not how I'm going to say it, because recursive really should be starting with the second term. Like in all the ones you did yesterday, they never gave you 4 terms, right? But I see what you're saying. If you want to say that, I won't write it. But I'm going to go like this because this is how the book says you should write it. And if you check your answers in the back of the book, I want you to make sure that you're matching it. Explicit sequence. Again, n is not going to change. You're trying to write the nth formula, but everything else should be a number. What does A represent? If you don't know, go back to the previous slide and look at it. Look at that whole slide and tell me, what does A represent? Right here. A is the first number. A plus D, that's some difference, but A is the first number. So to write your explicit formula, you have to put the first number in there, which is, in this case, negative 4. Do we know what D is? D is 5. And then I want you actually to simplify that, right? That's just a little algebra there. Multiply that 5 in there and combine my terms and make a nice formula there. Right? This would be negative 4 plus 5n minus 5. Or that would be 5n minus 9, not 59. which means we have found a formula for both the recursively defined sequence and the explicitly defined sequence. Go back to part B now. Which one is going to make the most sense? If we want to find the 10th term, I think that's what they asked us, isn't it? If we want to find the 10th term, you want to use the one where you have to use the one before it, or you want to use this one, where you can just plug it in? Yeah, every time. I skip this one every single time I do these problems until I get part D answered, because now it's really easy to find the 10th term. All I have to do is plug 10 in for n, and I get 50 minus 9, or 41. Do you have to do it that way? No, you can just work it out if you want. Do this second one over here if you haven't already. It's the exact same way, but just to make sure that we're on the same page here, we're just plugging in these formulas. So find the common difference, maybe skip part B for now, do the recursive sequence, which is going to be the same every time, you're just changing D, and then work out your explicit one and see if you can get the right answer. The recursive one, don't get thrown off by it. Just make sure you use the formula. It's just a sub n equals a sub n minus 1 plus your common difference, which in this case happens to be 3, but you do have to say n is greater than or equal to 2. Your explicit one should work out really nice most of the time, and I think if you simplify that right, I got 3n minus 8, and again, that's what I'm going to use to go back to part B to find the 10th term. That one would be 30 minus 8, or 22. Explicit formula is very nice to have. Questions about that? If you're adding or subtracting, this is what you do. But we also have those geometric sequences, and that's what the next slide is. Because for geometric sequences, we have our own little set of rules here, which is why probably you're not going to have to memorize all these for the test, but we'll see. And if you have a geometric sequence, you're not adding a number each time, you're multiplying a number. So notice it's kind of written the same way, but instead of adding a number each time, we're multiplying. And in geometric sequences, we call that the common ratio. So that first example I gave you, we were multiplying by 3 every time. So we had 3, and then 3 times 3 was 9, and then 3 times 9, or 3 times 3 squared would give you 27, and that works. And so, just like the common difference, R we call the common ratio, and if you know the first number, and if you know the common ratio, then you can write the explicit formula, which is always going to be a sub n is equal to a times r to the n minus 1, and the recursively defined one is still going to be a sub n, but you have to say use the one before it. And how do we write the one before it? We say a sub n minus 1, and we're still multiplying by r. For these, there's not much to simplify because you have some exponents. You can't do a whole lot with it. But again, it's just practicing taking the sequence and you writing the formulas. So let's just look at the next one here. Maybe I'll even double page this and see if we can. use this to do this one. Again, notice it says for each geometric sequence, part A, find the common ratio. Part B, find the 8th term. And again, I'm always going to skip part B. Part C, find the recursive rule. And then part D, find the explicit rule. And so, part A is, what am I doing to get to each number? I'm multiplying by 3, so that means that R equals 3. Something really important to point out, if you are dividing, you can't say dividing by 3 there. You have to write it as a fraction. If you were dividing by 3 each time, what would you write for your common ratio? 1/3. So whatever you're dividing by, you can just write that as a fraction. So that's an important thing to point out there. Part B, I'm going to skip. Part C, I'm just going to use this formula. And all I'm replacing is R. Because A sub n is going to stay as A sub n. A sub n minus 1 is always going to stay in that recursive sequence. It means use the one before it. So this would be A sub n minus 1 times R. Oh, that looks like an I there. Which happens to be 3. I'm going to erase that little dot. I like to write it, I wrote it how the book did it. I like to write it like this, because I like that 3 to be in front, but obviously those are the same thing. You can multiply in any way that you want. But just like the other recursive one, you have to say for n greater than or equal to 2. I don't like part C for part B because I don't want to have to find the 7th term in order to find the 8th term. That's what's recursive. You need the one before it. But part D is that explicit formula. And the explicit formula is much less work than the arithmetic one. Again, just like the arithmetic, you need, I'll write it out here again, A, which is the first term, times R to the n minus 1. And R is your common ratio. So A is my first term, which is 2. R is my common ratio, which is 3. And that's to the n minus 1 power. Make sure you're not breaking some math rules that you should know. You cannot multiply this together and say that's 6 to the n minus 1, because order of operations, you do exponents before you multiply. So you have to leave it like this. When you go back up to find that 8th term, you have to take 2 times 3 to the 8 minus 1, which is the 7th power, because it's n minus 1. 8 minus 1 is 7. You have to do 3 to the 7th first, and then you multiply by 2. So you have to make sure you don't simplify that wrong. That's going to be a pretty big number. $4,374. Questions about this? It's really just plugging into a formula, but it's kind of the opposite of what we did yesterday. Yesterday, they gave you the formula and you listed the numbers. Today, they list the numbers and you're listing the formulas. And we want to do number 4, but what would the common ratio be on 4? -1. So it would be the exact same thing, except for we would be plugging in -1 for R. Number 4 is one that you probably don't need to skip part B, because you probably can figure it out. The 8th term, notice that the 2nd and the 4th term are positive. These are odd. I think part B would just be +2 there. But this is the idea. We'll see where this goes tomorrow. I feel like I've lost lots of you to sleepy time. 12 through 20 even. That is the rest of day 9 for day 1. I'm fine if you just put this all on day 2. 12 through 20 even, and then 21, 24, 26, 27, 30, 31, 43 through 48. 21 and 24 are just like the common difference 26 and 27 are like the other ones, and then some other ones are some good thinking problems, and I'm sure we'll go over a few of these tomorrow. On 30 and 31, definitely you might want to go back and look in your books. There's some good examples there, but I'm sure we'll talk about at least one of those tomorrow. And then 43 through 48 are true, false, and multiple choice, so hopefully you'll be maybe okay on those. You do have like 5 minutes, so why don't you knock out that 12 through 20 even, which is the conversion diversion before you leave here.